Hello everyone, welcome to lecture 5 of week 7 of the course Power Network Analysis, in which we continue our discussion on the third last module, which is power flow analysis, in which we will today discuss what are these power flow equations, uh, how do we understand a step before solving these equations so that we can find the associated bus voltages, to be precise, bus voltage phasors in steady state for a given power network with respect to a reference terminal, for example, ground or neutral. And before we start solving this, there are certain classification of buses involved, which essentially comes in from these basic equations which come in as part of power flow analysis. So that's what we will discuss in today's discussion. In the previous lecture, we have finished our discussion on evaluation of bus admittance matrix, which forms a premise for power flow analysis. And we have also considered or understood the effect of considering mutually coupled impedances or admittances and transformer taps when they are in an off nominal position in the evaluation of bus admittance matrix. So, I request all to please go through the previous few lectures in order to have a better understanding, and then the discussion to come would become much clearer. So, in a way, to summarize, for a given n-bus power network where the network parameters are known, by network parameters I mean the line parameters, to be precise. The line parameters are evaluated or known as per the discussion held in module 4. Which was transmission line parameter evaluation. The line models are also known, and these parameters, they can be evaluated, the models can be estimated using some special exercise known as state estimation, which we briefly discussed about in the previous lecture. The transformer taps, positions, all those are known, available. The reactive power compensation devices, their settings are also known. To be precise, by reactive power compensation, I mean the capacitor settings, the capacitor banks positions, their values, the inductors, etc., etc. So, for a given n-bus network where all this information is known, the corresponding Y-bus, it is evaluated as per the discussion which we had earlier in the last two lectures, and this Y-bus turns out to be a n cross n matrix. It is not always symmetric, specifically in the case when transformer taps are at the off nominal position. Only when the transformer taps are at nominal position, or basically to be much more precise, if the transformer taps act as only voltage regulators and not as phase shifters, then the corresponding Y-bus turns out to be a symmetric matrix. And this Y-bus, as discussed, it correlates all n-bus current injections in terms of the n voltage phasors being measured with respect to a reference node, and this reference node does not exist. Its presence or numbering or labeling is not present in the Y-bus evaluation that we have seen earlier. So, given this Y-bus, our job is to find certain set of equations, which we call them as power flow equations, and from them we will be able to find the corresponding bus voltage phasors. If we know the bus voltage phasors, then we can use Y-bus and voltage phasors to find the corresponding currents at all buses, from where then all other relevant quantities can be known. So, when we talk about these voltages, voltage, they are, as I have already mentioned, these are voltage phasors. So, a phasor is actually a complex quantity or a complex number in time domain, which can have two forms of representation. One is a polar representation and the other is known as rectangular representation. These representations, they vary as per this notation, where in polar form every phasor has a magnitude, which we call as voltage RMS value essentially, and the corresponding phase angle theta I is being measured with respect to a reference, which is the reference node, whose presence is not there at all in the Y-bus. Now this polar quantity or voltage phasor, to be very precise in terms of mathematical notion, Vi mod at an angle theta I is actually equal to Vi mod e to the power j theta I, where e is the exponential number, not the e which is present over here. Please don't confuse this e with this e. This is the actual exponent, the natural exponent based on which the natural logarithmic terms are evaluated. And j here is the complex operator, which is minus root over of -1. This number can also be expanded in terms of cos of theta I plus j sin theta I, wherein we had a polar representation of a complex number, which when segregated into relevant real and imaginary parts gives us the analogous rectangular representation of the same complex number. So depending on how are we representing our voltage phasors, whether they have a pure magnitude or the phase angle, or they have the relevant real component and imaginary component, EI and FI. EI is real part of VI phasor, whereas FI is imaginary part of the complex number, which is Vi, and EI is actually Vi mod cos theta I, whereas Fi is Vi mod sin theta I. So depending on whether the polar representation is being used or the rectangular representation is being used, the corresponding voltage variables that would come in, they may be different in power flow equation. So basically in polar form, you would only have a magnitude as and a phase angle, whereas in rectangular form, you would have the real component and the imaginary component, which again can be correlated with the voltage magnitude and voltage phasor correspondingly. So essentially, depending on what type of representation for the voltages is being used, the corresponding equations that we would see would also vary accordingly. So given that we will usually start with the polar form of representation in today's discussion, and towards the end we will see how a rectangular version of voltage phasors lead to relevant equations. So assuming that this voltage has a form of this polar form where magnitude and angle need not be known, and purpose of power flow is to find these unknown quantities. If suppose we know those quantities, then essentially we can find the currents at every bus, again based on the Y bus definition. For the kth bus, if we have to find, or sorry, for the ith bus, if I have to find the bus current, which again is a complex number, actually it's a phasor. This can be represented in terms of the corresponding Y bus elements and the all n voltage phasors in this form, where every such Y bus element, which again is a complex matrix, can have the associated real component, which is G, real part of Yik, and a corresponding B matrix, where I comma k refers to the imaginary Bik refers to the imaginary part of Yik. So essentially we can have G and B matrices, which are again n cross n matrix in themselves, and these are actually equal to real part of Y bus, whereas B is equal to imaginary part of Y bus. So we can also separate these two real and imaginary parts. So essentially G and B, they are actually all real numbers. There is no imaginary component or complex component present in capital G and capital B matrices. So if we know these current injections, then we can also evaluate the complex power at every node. We have seen this expression of complex power in our first module, which was basic circuit principles, where we have seen that complex power is product of voltage phasor and conjugate of current phasor. For the sake of our convenience, I have intently evaluated conjugate of complex phasor. So the conjugate, instead of appearing over current, essentially is coming over here. So basically, if SI is VI into II conjugate, then SI conjugate would be VI II conjugate whole conjugate, which when broken up becomes VI conjugate II conjugate conjugate. Double conjugate doesn't change the sign of II actually. So II double conjugate is simply equal to II. So that's how the current expression is. And I have simply substituted the II current expression into this expression over here, wherein I can get a summation form. Now, YIK can also have its own individual real and imaginary parts, and depending on whether voltage is being considered in polar form or rectangular form, the expression of SI conjugate in polar form looks something of this order, whereas if VI and VK are having rectangular forms as EI plus JFI, VK as EK plus JFK, then if we substitute these numbers into this expression and expand them up, we would get a complex form of this form, which is where the rectangular coordinate for complex conjugate power can be evaluated. And remember, SI is actually PI plus JQI, where PI is real power and QI is reactive power. So essentially what I am trying to say is we can take corresponding real and imaginary parts of these entire summation terms and also analogously get PI and QI expressions, which we will see in the next few slides. Before we do that, I had also briefly discussed that why should SI be equal to VI conjugate? Why not any other combination like only VI or V into I whole conjugate or V conjugate into I? The answer to that lies in the discussion that we will have in this particular slide, that why SI is not a simple product or a entire conjugate of a product. The reason for that, which I had already mentioned in the first module, was the intent of having this conjugate appearing in either on voltage or current is to make sure that the power which we are evaluating, be it real power or reactive power or complex power, these are all average quantities. If you recollect the definition of real power, it is actually the average of instantaneous power. And when we say average power, it has to be a quantity which is going to be independent of time. Remember, our voltage and current phasors, they can have their own time domain representations. And if we want to convert a time domain signal into frequency domain, we have to choose a frequency component or a frequency signal as a phasor, where actually sine omega t or cos omega t, where omega is that frequency, the source frequency based on which the reference is to be chosen. So VI and II, they are actually time varying quantities. In phasor domain, they appear to be steady state quantities or time invariant quantities. But when we are trying to find average power, the average power should be independent of time. To make sure that this independency comes in when we are evaluating the average power, there is a need to sort of get rid of this frequency domain reference, which is the basis for evaluating V and I. When we take conjugate either on VI or II, the conjugate part is sort of, so what does the conjugate do? Conjugate essentially changes the sign of the phase angle of the phasor. If the angle is plus theta I for current, I conjugate would have minus theta I as the angle, and the same I conjugate, when it is represented in time domain quantity, the corresponding sine omega t which was chosen as a reference would now become sine of minus omega t. So to get rid of the frequency dependency or the phasor dependency, one of these quantities should have a conjugate, so that the power which is measured, the average power, it remains time invariant. And to give you a more precise example, so basically that's the reason why one of these combinations could be a possible combination for complex power, and definitely not these would serve, because here the frequency dependency, which is the reference for the voltage and current phasors, that is not getting rid of. The other secondary example is that if we have a 1 kilowatt resistor, let's say a purely resistive bulb or incandescent bulb, if it is rated at 1 kilowatt at, let's say, 230 volt voltage, And this 230 volt voltage at one point of time, let's say in India, is at source frequency 50 hertz, or let's say in US or Canada, the source frequency is 60 hertz. The bulb, no matter whether it is connected in India or US, will still consume 1 kilowatt if the voltage rating is 230 volt, which was its rated voltage. So that gives another notion or example that why the average power in actual quantities need to be time invariant, and that's how the notion of rated power or rated quantities or rated MVA etc. is defined. So one of these combinations has to be true, which is the conjugate present over here. The secondary reason why often SI is equal to the VI into II conjugate is as per the definition of power factor. A day, if it comes that our inductors would be called as those devices which deliver reactive power, and capacitors would be called as those devices which consume reactive power, essentially changing the notation of power factor, then on that day, maybe SI would also be equal to VI conjugate into II. For time being, our power factor convention has not changed. We still associate inductors to be reactive power absorbing devices, capacitors to be reactive power delivery devices. So SI is called as VI into II conjugate. Going ahead, if we assume our voltages to be in polar coordinates, we have seen this expression of complex power, which is the conjugate complex power. From there, we can separate out the real part as well as imaginary part, and we call these equations to be alpha and beta. I'm not going to spend much time on how these are to be evaluated, but I can just give you a brief indication how this can be done. So Vi mod, Vk mod, they are in themselves scalar quantities, they are not complex numbers. We have two complex numbers here. One is this complex number, the other one is inherently sitting here as 1 at an angle theta k minus theta I. So 1 at an angle theta k minus theta I when expanded would become cos of theta k minus theta I plus j sin theta k minus theta I. And when this complex number gets multiplied with this entire complex number, it would give us gik cos of theta k minus theta I minus, or let me expand it further, plus j gik sin theta k minus theta I plus j bik cos of theta k minus theta I plus j square bik sin of theta k minus theta I. Remember, j was root over of minus 1, so j square is minus 1. So this term here actually becomes bik minus, and overall the product has this as the real component, and if I take out j separately, then this becomes the imaginary component. So that the associated terms actually sit in the real part and the associated terms appear in the imaginary part. So that's how you can get real and reactive power expressions. We would please note these equation numbers alpha and beta. Alpha refer to real power equations, beta would refer to reactive power equations. And since SI conjugate is Pi minus JQI, so this minus sign is actually appearing over here in the minus sign. So given a bus I, which can be connected to several other buses like bus K, bus M, bus N, because our power network is actually a mesh network, wherein the bus I has a generator connected to it and also a load connected to it. Remember, our generator injections are considered to be positive because the generator is feeding in power into the network from the source end, whereas a load injection is considered as negative because it is consuming power from the network into itself. So because of the change in notation or sign of currents, the way they deliver and absorb power, the corresponding injections are respectively positive and negative for generator and load. Given a bus, if I have bus I where there is a generator which is generating PGI real power, there is a demand which is consuming PDI as the real power demand, then by KCL, in KCL might be a wrong word, but if we apply analogy of Kirchhoff's current law, let's say Kirchhoff's equation, which says that whatever is the net current into a bus, the same current should go out of the bus, maybe through different parallel paths. If the same logic is applied here for power, then what we see here is that the generator is anyway generating PGI power into this bus, and at the same bus there is a demand which is consuming PDI power. PGI and PDI, they need not be same. They may be different. In fact, PGI may be less, maybe more compared to PDI. Then resultant difference in power, which is, let's say, PGI minus PDI. If PGI is positive, that is, it is generating more power than the demand itself, where can this power go? The excess of real power, which is PGI minus PDI, where it has to go? It has to go somewhere, because power, like energy, cannot be created or destroyed. There is no other storage device which we are considering. So this power has to go somewhere. It cannot be stored itself at the bus, because the bus itself is not a power storing device. So this power actually goes to neighboring buses through these transmission lines, which are marked as I, K, I, M and I, N. And the corresponding real power flows, which are PIK, PIM, PIN, they should together add up to this particular injection, because as per conservation of energy or conservation of power, excess power if it is present or deficit power if it is present, it has to be accounted as flows into the network, because we are not considering any storage device at all on bus I. So what happens is that as per the notation or thought process of solving power flow equations, Pi is always equal to PGI minus PDI. By solving power flow, we are ensuring that Pi should become equal to PIK plus PIM and PIN. So maybe if I were to sort of simplify this, there are two boxes which I am marking. This is inherently true. Nothing needs to be done exclusively before solving power flow. This has to be naturally true or inherently true. What we are trying to serve in power flow is to ensure that this equation becomes true, and this is done via power flow analysis. This doesn't become true naturally. It has to be done through power flow equation, and that's where power flow actually finds what should be the corresponding voltage phasor at bus I, bus K, bus M and bus N, so that this equation becomes true. This is only from the perspective of real power flow. The same logic would be applicable if we talk about reactive power at respective buses. So given this understanding that injections, they are naturally or inherently true, power flow essentially tries to find the bus voltage phasors at all buses, so that the corresponding conservation of power aspect becomes true from real power and reactive power perspective. That is the basic premise of power flow analysis. So if we were to sort of see what type of equations we are handling, if we are talking only about polar coordinate version of voltages, then every such bus will have two equations, alpha and beta. When we say equations, our equations naturally should be in form of real numbers. Voltages actually are complex numbers. So every complex number has two real parts, one real part and the other real part is the imaginary part. So if we remove the j part out of imaginary part, it also becomes a real part. We are trying to solve real equations to find real solutions. So alpha and beta, can exist for every such bus or node, where capital G and capital B are in terms of network parameters and voltage phasors which are unknown. The parameters, they are known from manufacturer data, and there is a optimization exercise which also helps letting know the network topology and states, which is known as state estimation. And purpose of power flow is to find all these voltage phasors. So if we were to look at every such bus, let's say bus I, then each bus only has two equations, alpha and beta, and each bus also has only four variables, which is, what are those variables? Those four variables are the bus voltage itself, the bus angle itself, and the corresponding injections which have to be equated with respect to respective line flows. So there is a dilemma in this situation, that Vi and theta I are the first two independent variables, and Pi and Qi are the consequent dependent variables which should be equated with the corresponding real power flows. So every such bus has two equations and four variables, and it is pretty common or obvious that if the number of unknowns are more than the number of equations, we cannot find a unique set of solution for those unknowns. So there has to be some other mechanism or process which has to be followed. The process is that for two equations available, we can at best uniquely solve for only two variables, provided the other two are chosen, fixed, or known in some way or the other. So in general, if we talk about load, PDI and QDI, they are uncontrollable quantities because it depends on the consumer whether the consumer wants to consume power or not. So PDI and QDI, they are not in actual operator's control. Often PDI is known, and using the respective load model, one can estimate what would have been the corresponding QDI. PDI and QDI, the demands, they are generally known from the load forecasting exercise. And our generations, they tend to follow this load because the purpose of generation is to meet the power demand. So if load is known from forecasting, generations also have to follow this load, and hence they are called as controllable quantities, whereas load is called as an uncontrollable quantity. PGII is usually known from this economic dispatch problem which we have discussed in the previous lecture, so that the cost of real power generation is as minimum as possible. And it is further fine-tuned by automatic load frequency control or generation control, which we also discussed during synchronous generator discussion for small load variations. This is all for real power generation. Usually the same is not true for reactive power generation. In fact, reactive power generation specifications are very rare. What is actually, and the reason for that is, by using power factor control or excitation control of a synchronous generator, the reactive power generation can be regulated. The generator may absorb reactive power as well as deliver reactive power, which may in a way regulate the terminal voltage of the generator. So indirectly, the terminal voltage of generators, they are specified in terms of set points other than the reactive power generation. And these terminal voltage set points, they are also obtained from a optimization exercise known as active power loss minimization, which we discussed in the previous lecture also. And the purpose of this objective or exercise is to find voltages or have voltage profiles in the network which are almost flat or uniform to each other, so that the corresponding potential difference across lines in the power network is as minimum as possible, so that the corresponding power loss, in a way, not the power flow. The bus voltages do regulate the power flow, but with the intent to have minimum power loss in the active power loss in the network. So as I mentioned, active power loss minimization, it's a separate exercise similar to economic dispatch, which helps in telling what should be the terminal voltages of the synchronous generators, which are again regulated or controlled by another automatic loop known as automatic voltage regulator, which we have not discussed at length in this particular course. It's a control loop or feedback loop, closed loop feedback, very similar to automatic load frequency control or generation control. So essentially, for buses where generators are connected, what we can know from the optimization and related optimization exercise is that the terminal voltage of a generator can be specified. Its set point can be changed as per the reactive power control or excitation control of the synchronous generator, and the corresponding real power output can be known depending on the economics involved. And based on this terminal voltage, I mean, there's always an upper cap of what can be the minimum or maximum power factor control which is available for a given synchronous generator, which in a way comes from the capability curve which we have discussed. So every such synchronous generator, based on the capability curve or the available power factor control exercise, can be replicated or stated in terms of minimum and maximum reactive power generation. How much is the minimum reactive power which the generator can generate or absorb or deliver, and vice versa for the maximum number depending on the capability curve of a synchronous generator. So that leads to our premise for classification. To sort of summarize before I explain what type of buses do we have. We have lot many unknowns, we have less number of equations in power flow, so there has to be a way of fixing some of these variables for every such bus so that the number of equations to be solved becomes same as the number of unknowns, and that leads to this discussion of what can be known and what can be unknown in power flow analysis. In a nutshell, PDI, demand, real power demand, and reactive power demand, they can be known from load forecasting exercise. PGI can be known from, so let's say if I call this as load forecasting exercise. PGI can be known from economic dispatch exercise as per system economics. Terminal voltage of generator buses, they can also be known from active power loss minimization via voltage profile control. If these quantities can be known by some judgment, some mathematics, some optimization, then maybe we should make use of this information and try to have a match between knowns and unknowns in power flow. And that in a way leads to the part of classification of buses, in power flow analysis, wherein we have our most common bus, which is called as the load bus or PQ bus. As the term says, load bus or PQ bus, there is definitely no generator connected to such a bus. If there is a generator connected to such a bus, then in that case, PGI and voltages become known, and hence it doesn't remain as a load bus anymore. It might happen there is a bus which has nothing connected to it. It has just few incoming lines and few outgoing lines. There is no generator connected to it. There is no load connected to it. Those buses could also be called as load buses or PQ buses, or also to be in fact zero injection buses. And the reason why we call them as PQ bus, we'll see that in a moment. The explanation for load bus, I think it is pretty evident. It only has a load connected to it. The load itself could be zero. There is no generator connected to such a bus. And once the load is known, the load bus type is known, then in that case, PDI and QDI, they are known from load forecasting. So for such a load bus, if we have to see what is the injection at the corresponding ith load bus, since there is no generator connected to the load bus, so PGI is not present, so it is actually zero. So PI is simply equal to minus PDI, and on similar lines, the injection at ith load bus is only minus QDI because QDI is a demand. So if the injections are now known, which are known from the load forecasting exercise, and we put them in equations alpha and beta, then essentially we have a P equation and a Q equation, and this P and Q essentially also when combined give it a name of PQ bus, because for a PQ bus the P injection and Q injection values are already known. So the LHS part here is known. What is unknown is the quantity sitting in the RHS, and essentially for two equations we have in a way reduced these two unknowns. We only have two unknowns. Those unknowns are voltage magnitude and corresponding phase angle with respect to a reference phasor. So we have two equations, alpha and beta. To segregate or signify those equations for a PQ bus, I have used a subscript PQ sitting over here just to ensure that these refer to PQ buses only. There are two equations for every such PQ bus, and there are only two unknowns for every such PQ bus. So in a way we have tried to have consistency or ensure consistency between the number of equations and number of unknowns for one such classification of bus, which is known as load bus. We'll continue this discussion in the next lecture, where we will expand on classification of buses and look at what other buses can exist, and also we'll sort of continue with the equations part of rectangular equation and so on. Thank you.